Great. So thank you. Thank you for being here. So I'm Guillaume. I'm French. You can hear that from my voice. And today it's a bit special for me because Niels asked me to do a keynote. So at first I kind of said no. I don't have time. It will take time, a lot of time to prepare, and indeed took a lot of time to prepare. Yet I'm super happy to be here. And the idea today is to go back in time, like 20 years back in time, and to have a look at the IPv6 support in Scapy. So briefly, who am I? Today, I'm a cybersecurity researcher at GitGuardian. That's a company that does secret detection. So basically what I do, I look for secrets everywhere, Docker Hub, GitHub, GitLab, any place where people can hardcode secrets, because that's what we do, secret lifecycle and detection. Next point is only relevant if you are French or if you can read French. I'm also the editor-in-chief of a magazine called MISC, dedicated to cybersecurity. So every 2 months, I'm looking for articles. So if you happen to know someone that can write in French, or if you want to write in French, I'm always looking for authors. And I will say on my spare time, because I don't do that much for a living, I really enjoy parsing data, reversing binary like firmwares, network protocols, and basically every time there is some kind of embedded system, I'm trying to dump the firmware and have a look at it. Scapy and me, I've been a user since 2004. That's around when Philippe created the project. I have to confess, I didn't really like Python that much back then. I changed my mind, so I do a lot of Python. Why? Because I didn't like the fact that the language is actually trying to push you to do this and that. You don't use brackets and so on. So at first, yeah, it's really weird. I want to do what I want, but I think it's a pretty good design. And also because I start Python with Scapy, and the code is, I will say, a bit difficult to learn. There's a big step to learn. So at first, I was not really a Python guy. Philippe asked me years later, 2013, to be a maintainer. So I tried to do my best. Currently, I'm not doing much. The main maintainer, the lead maintainer, as we call him, is Gabriel Potter. So he's doing a lot of work to maintain the project, trying to fix stuff, maintain issues, do new PR, and he did an amazing job in the last 3 years to introduce really good Windows support, Windows protocol support in Scapy. So it's a bit fun the way across time, across like 23 years in Scapy lifetime, we all contributed to a project in some part of another. So what I did was mainly IPv6. That's one of my main contributions that I did with another French guy called Arnaud. I also contributed to the BSD support. When I started with Scapy, Scapy was only natively supporting Linux, which means that you can just copy the scapy.py file on Linux and then start crafting packets. And BSD, it was more difficult. You had to install pcap, dnet, and from time to time, it was not working properly on OpenBSD and so on. So for me, it was a bit frustrating. So what I did, I implemented what we call the BPF architecture, which is basically the subsystem in BSD that allows you to send and read packets. More recently, I work on the pcap-ng writing part. Another maintainer did the reading, and the writing part is really cool. The format is a bit complex. Pcap-ng, it's just to store packets, but you have options, blocks, and so on, and Scapy is able to read all of that and write that. For example, you can write a comment associated to a packet in pcap, and then later on read it with Wireshark, which is really great. And because we have the pcap-ng support, we can do super cool stuff. In pcap-ng, you can store keys, like TLS keys, in a specific block called secrets. And what you will do with that, you can sniff a TLS connection. You will write the session keys in the pcap file, and if you open the pcap file with Scapy, Scapy will decrypt the file for you. So it's really convenient to do TLS. And then, as Philippe said, as a maintainer, I try to do some other stuff which are not fun at all. The first part was to improve the coverage and the unit tests. And this was really important. So we go at that time from 30%, if I recall correctly, to 85, 83 today. It was really important for us because we were in kind of questioning to support Python 3, or actually move to another piece of code that Philippe developed, which was called Scapy 3. That actually never happened. So unit test was a big part of the project. Then when we moved to GitHub, we decided to use the CI, namely GitHub Actions, And the goal was to actually, for every commit, run the test on many versions of Python, Windows, Linux, and macOS, which made the project more robust. And finally, we did a lot of work on the PEP 8, which is basically having a clean code base with no funky indentation and naming and so on, which is also a big part of what I did at that time, and the Python 3 support. At first, we decided to support both Python 2 and Python 3, which was a really difficult task because when it comes to manipulating network packets, I can say that Python 3 and Python 3 are incompatible. So we decided to have both. And we had one rule, I did a few rules, was to keep maintaining Python 2 until it was too complicated to have it in CI. And that happened with an Ubuntu release when they dropped Python 2.7. So we decided to actually drop Python 2 support and only do Python 3. So today, Scapy only works on Python 3. But we are really proud to keep the support of Python 2, not because Python 2 is cool, but because Scapy is a tool for hackers. And most of the time when you hack, you end up with a really old system, really old Linux kernel, like 2.6, with a really old Python interpreter. So having people tweak Scapy to use Python 2 was not good for us. We wanted to actually give you the power of hacking on Python 2 as long as possible. So today I'm here to talk about IPv6, and this timeline is interesting. We won't go into all of the lines. So the Python support was introduced 20 years ago indeed, 2005. Some other dates to have in mind, 95, that's the first IPv6 specification. 1996, the initial Linux implementation, and also something called the 6bone, which was a worldwide IPv6 test network, which was a big part of the IPv6 initiative. And finally, the last days I will comment to that 2001, that's when Cisco and Microsoft introduced the commercial support of IPv6. So it was a long time ago. And when we started the IPv6 implementation, at first it was a game, and then, and that I will describe in the next part, we found some vulnerabilities on the way. And for us, it was just, let's put it that way, that IPv6 was not really ready to be exposed to people and security researchers at that time. So Scapy, that's Scapy in what are supposed to be Japanese. That's part of an email that I sent to Philippe on June 7, 2005. That's an implementation, the first implementation of IPv6 Scapy I did when I was living in Tokyo. And here, what you are looking at is just a ping, so echo request of my laptop to my server. At that time was called Nama. In fact, it was Nama Biru, which means draft beer in Japanese. So here, just saying 3 echo requests and getting 3 echo replies. So it was the first working implementation of IPv6 Scapy, which looks simple, but in the end you have a lot of codes, a lot of changes because IPv4 and IPv6 are basically incompatible. This was the initial IPv6 packet, not super interesting. The fields in green, the one remaining in the code today. The rest changed. We changed the names, we changed the types, but still we have the version, traffic control, flow label, and the packet length. So that's a piece of codes, so character type 20 years ago that are still surviving. The real origin, that's a file that I call scapy-dev.py, which was a patch for a former version of Scapy released in March 2005. That's something that I did during my PhD in Tokyo, and more specifically, I was working in May 2005 in Network Interop in Tokyo. So it's a big exhibition of network vendors, network operators, basically in a big hall demonstrating what are the new stuff in networking. So my day was actually that, moving around in the main hall with the map of the network and trying to debug connectivity. So basically plugging the laptop, configuring a VLAN, making sure that we have connectivity both ways, it was fast enough, that we have IPv4 and IPv6 and so on. And most of my day was actually to wait for an incident and go around the hall and fix stuff with my team. I was kind of bored, so for me, it was really a good opportunity to have a look at the network with not Wireshark at that time, it was called Etherreal, that's before they renamed it, before the main Etherreal developer moved from one company to another, and then to rename the tool. And I was watching IPv6, like trying to do a WebGet and ping6 and trying to discover IPv6. And then basically the first Scapy dev implementation was looking at Wireshark, reading some pieces of the RFC, and luckily after 2 weeks, I put everything together. It was only working on Linux. That's why later I did the BSD implementation. And again, I was not a Python guy, so everything was a bit funky, indentation, naming, and so on. But still, at the end, it worked, and I sent it to Philippe. Something a bit bigger happened at the same time. Philippe was working with a French guy called Arnaud Ebala, so we became friends since. And Arnaud was also working on an IPv6 implementation. So we decided to merge our patches together in something that we later called Scapy6.py. So that's something we did in December 2005. And the goal of Scapy6.py was to be independent, in the sense that with minimal changes to Scapy.py, you can call Scapy6.py and have IPv6 working. And mainly for us, the goal was to move fast, implement things without having to push everything through Philippe, because at that time we didn't use Git, we didn't use GitHub, and basically we had to send patches to Philippe. Philippe will apply the patch to Scapy and publish it. So it was not super efficient. So at first, the support was super simple. So of course, we have IPv6, TCP, UDP, DNS. It's a bit different, the way you ask for an IPv6 address. ICMPv6, all of the flavors, echo request, echo reply. Something called NDP, Neighbor Discovery Protocol, which replaced ARP, which is the biggest difference with v6 and Trasog 6. And also, still in the code today, it's really weird, some very personal features. So here you have a function that will create a tunnel with IPv6 on top of IPv4. And I was doing that, using that in my apartment in Tokyo just to do tests and having connectivity. And this address was the address of my server in Japan. So it's still in the code. Forgot to remove that. On the right side, just a funny picture of a cable, network cable, Ethernet cable. And here it's written that it's IPv6 compatible. Indeed, it's not that weird. What you have to know on top, the red, green, and blue boxes, that's the name of network operators. One of them is YahooBB, Yahoo Broadband. That was my operator. And at that time, when you get connectivity in Japan, you get these network devices, boxes, and some of the vendors have the IPv4 Ethernet port and IPv6. So basically, what it says that if you plug this cable, you will get IPv6. It's a bit weird, but that's the way they actually sold and pushed IPv6 20 years ago to customers in Japan. So briefly, what I will call IPv6 essentials, the main part, not on the slide, it's purely incompatible. So you will need, if you want to do IPv6, you will need an IPv6 stack, you will need an IPv6 network, IPv6 router, so you need to duplicate everything. So what people know the most, that the addresses, they go for 32 bits, super easy to read, 1.2.3.4 to 128 bits, and something like that, which is difficult because you have to say 2001, colon, DBL, colon, and so on. Super difficult to read. There is no network address translation, which is for network architect, security architect, really good. Because you only need to focus on firewalling. And why? Because there is enough addresses to accommodate all use cases. So you can have addresses locally, you don't have clashes of everyone is using the 10/8 prefix, so that's really nice. ARP, so Address Resolution Protocol, was replaced by NDP, much more complicated. It's not using broadcast anymore, it uses multicast, and it's not on layer 2, so not on top of Ethernet, it's on top of IPv6. So that's a big change. For security people, for attackers, for people doing defense, it's pretty much the same attacks, just different names. Yep. So here I tried on this slide to discuss the good and bad design choices that we made with Arnaud at that time. The good ones, we decided, I think Arnaud did it, to have compilations to group similar headers, ICMPv6. So if you type ICMPv6 and press tab twice, that will give you echo replay, echo, NDP, and so on. So all of them are we sorted out in altogether. Same stuff for IPv6 extension headers. So if you know the trick, it's really simple to go inside the IPv6 implementation and find what you need. The other good part is mainly based on Scapy. We have default values that works, and here that's a packet that will actually do something really useful. So here you don't need to specify anything for Ethernet. Scapy will take care of finding the MAC, source and destination addresses. Same stuff for IPv6. And finally on top, you put something called router solicitation. That's a specific IPv6 packet that you send to discover the router on the network. And then if there is one router, it will answer with a router advertisement with the prefix that you need to use. It's basically a replacement for DHCP. On the other part, some really bad choices. In Scapy, you have something called conf.iface that will tell Scapy which network interface it should use. For example, what is doing MAC address resolution. And for some weird reason, at that time it was because we had one interface with IPv4 and another one with IPv6 and wanted to be able to use the two at the same time. We decided to use conf.iface6. But in the long term, it was really confusing. So we had a lot of issues, a lot of questions. We had to fix documentation because you will never know if you have to use iface6 or iface. So we decided to remove it. So today, you just use conf.iface, and then Scapy will send the packets where it should. So the other bad part is that the Scapy layers inet6.py file is really big, 4,000 lines long. So when we splitted Scapy from the main scapy.py file to the smaller, the Scapy2 with many different files, we didn't split inet6.py. It's a big file, so maybe it's not the best design choice. And maybe sub-protocols like NDP or Net Information Query or other ones should have been separated. It's still a beast. But okay, I know my way in the file, so I'm fine, but for newcomers, it might be more difficult. Something that I did at that time, every time I was doing a change in Scapy, so reading a RFC, reading a draft, I was doing changes, and every day I was breaking Scapy. It was a bit annoying, so I did something that I call regression6.py. It was mainly a way for me to have unit tests. Unit tests, why? To avoid regressions when I was adding feature. So it was weird. Weird piece of software. It didn't survive that long. So it was in 2005. That's actually the same year that PyTest was created. So it means that was not much tools doing a unit test. So this one is basically, I will give this tool a packet. The tool will send the packets or pretend to send the packets and actually receive an answer and part the answer. And later on, Philippe did something way nicer, which is called UT-Scapy for unit test Scapy, and that's the unit test system that we are still using today. Maybe if we have time, we can remove UT-Scapy and again, to be more in the Python ecosystem, use something like PyTest. But as of today, our tests are written in UT-Scapy, which is basically Python with some markups which are specific to UT-Scapy. Another big part of what we did 20 or 19 years ago was implementing mobile IPv6. That was part of my PhD that I did in Tokyo, and Arnaud was also working on mobile IPv6 at the same time, and I think that's why both of us got interested into IPv6. So why? Because mobile IPv6, it's a dead protocol basically. No one is using it today. But it was super cool. So the promise was to allow device, like my laptop, to keep the same IPv6 address while moving. Like a VPN, except that you will maintain your TCP session, UDP session, people can send you packets wherever you go on the internet. So what I was explaining at that time, it's basically like your mobile phone. When you go from what I did from France to Germany, I keep the same phone number. Anyone can call me on the same phone number, and mobile IPv6 the same. You keep the same address, people can reach you. And Arnaud did a lot of work with mobile IPv6. He put a lot of energy to implement the IPv6 support, to bridge everything together in the Linux kernel. And he was doing cool demo at that time in conferences. He will actually stream a video and move his laptop connectivity from Wi-Fi to mobile, then to Ethernet and back without losing much frames. So that's really, really nice. There was an interesting feature in mobile IPv6 called route optimization, and it will allow node-to-node communication. So it was really important because if you have a friend in Tokyo, you are living in Tokyo, but your VPN server, which is called Home Agent, is in Paris, obviously your packet will go from Tokyo to Paris and from Paris to Tokyo. So you will lose a lot of time. And this route optimization was a really cool feature just to be able to make these mobile nodes talk together from Tokyo to Tokyo. And that was part of my PhD. That's mainly why I implemented mobile IPv6 in Scapy. The goal was to simulate mobile nodes to do my PhD thesis around the world. So why? Because people will give me kindly access to virtual machines like OpenBSD, FreeBSD, and sometimes more exotic system. But obviously, none of this system was supporting mobile IPv6 because you have to implement that in kernel. And for me, Scapy was a way to simulate mobile IPv6 to do measurements and see the optimization that we'll get by changing some things and tweaking route optimization. Again, the protocol is not used anymore. So why I'm talking about that is that on the way to playing with IPv6, reading RFC, implementing it in Scapy, also implementing mobile IPv6, we actually found some gems and really cool stuff in the RFC. So IPv6 routing header, that's a big name for saying source routing. It was banned in IPv4. So what is that? Source routing was a way in IPv4 for a node, like my laptop, to say, actually, I want to specify the list of routers that my packet will go through instead of letting the network do its stuff. So on this simple network architecture, that's a figure that we used 20 years ago. That's why you have really old iMacs. Regular internet will send the packets on the red path because it's short. So it's not actually the way networking works, but here let's pretend it works like that. So we'll go on top. And source routing is just a way for the iMac on the left to say, okay, I want the packet to take the shorter path to go to the red daemon and then to the small penguin. That's source routing. It's really weird, but it was in IPv4. People found out that it was stupid, they removed it, and guess what? Some other smart people, they put it back in IPv6. But there's a tweak. You can actually put more hops, more routers, 127. So it was a big list. And this is a really good example of something that looked kind of safe at first. I mean, okay, that's weird, but people could specify the source routing, yet it was super complex. It was 50% in lines of the IPv6 specification. So when we discovered that with Arno, we kind of say, okay, that's a bit weird. We are kind of suspicious. And what I will present in the next slide, that's something that, again, looks safe, but really highlights that IPv6 stacks, they were not ready to be exposed to people like us trying to break stuff. And on top of that, because the implementation and the specification was so weird, so complicated, it was hard to tell if only routers should process it or if host should process it. And that's what Arno discovered. He did a bunch of tests, and he discovered that the implementation actually processed the routing header type 0. And he found a way, really cool way, to bypass firewalls. So that's a figure from Arno at that time. So here the attacker will craft a specific packets and trying to bypass the firewall to be able to talk to an internal server. The trick is the host must process routing header type 0, so it's not the case anymore. So in that example, we want the www external web server to process the routing header type 0, and then the attacker wants to connect to www internal by doing a specific IPv6 packet. So what you will do, you will send the packet first to www external, this one, then it will use a routing header, just need to put the address of the next hop, the next target, and then TCP on top. And when this packet reach www external, the kernel here will actually switch the destination address and the first element in the address list and send forward the packet to the WW internal website. And then the website will send the answer back to the attacker. And depending on the firewall behavior, yeah, you can bypass the firewall. I won't go into detail of the extension header routing, but basically inside you also have a field called offset, which is a pointer to the element in the list that you will need to use to do the switch between the addresses list element and the destination. So that's the first issue that Arnaud discovered. And then we had a game, and the game was to find a packet and the list of hosts, a list of addresses that will take the longer time to receive an answer. So the game was, I was looking for addresses. I will send it to Arnaud and say, okay, this packet will be back in 1 minute, 2 minutes. So we did a game like that for several days. One day Arnaud came back and said, okay, if you send this packet, the answer will get back after 10 minutes. Okay, guy, you won, you killed the game. So basically, we'll send an SCMP echo request and the answer will get back to you 10 minutes later. And so why? Because he found 2 routers so far that if you put a super long list, here there is an error, it's not 2, it should be 62 or something like that, way, way bigger. The packet will bounce forever and at some point will go back to you. And it was, as an attacker, also a way to amplify network traffic. You will make a packet loop between 2 routers, R1 and R2, and at some point the packet will be delivered to the target. And the amplification was 88-fold, so it was really, really big. That's because the list of address is big, and actually not this one. It should be 42 if I'm correct. So here what you will do, you will put the first destination R1, and then in addresses R2, R1, R2, R1, R2, R1. That's what this does in Python. Duplicate the list, in that example 2 times, and then you pull the target. So the packet will bounce in between router 1 and router 2 and get delivered to target. So what we also found, Arnaud found that could make a Cisco router crash. So not exactly this one, but the Cisco router will crash if you put destination R1, so Cisco router, and addresses only him. So the packet will loop internally, and then the iOS will crash. And the bad part is that it's still the same case today, but most of the network operators, even though IPv4 and IPv6 are incompatible, they don't deploy 2 networks. They have 1 router, big stuff that does IPv4 and IPv6. So it means that in that case, we'll actually crash the router by using IPv6, and the IPv4 part will also die. So that was initially reported to Cisco in early 2006. So just when we did the first implementation of Scapy, it took 1 year for Cisco to actually fix that. It was really huge and bad. And that will make me go to the next slide. Next slide is the deprecation of the routing header type 0. That's a super funny story. Philippe here and Arnaud, they did a presentation in a conference called CanSequest in Vancouver in April 2007. So that's why it's 2007 and not 2006. That's because it took Cisco 1 year to fix, and after the fix, they decided to go public and do the presentation. But we knew the issue for 1 year. We kind of communicated about the amplification effect to some network operators who were friends working at Colt at this time, so they kind of knew, so they started to filter some IPv6 extensions, but it was not public yet. So they did a presentation in April. The RFC was published in December. Took a lot of time, but that's the way it goes with ITF. You go from a draft and revisions and then the RFC. So it's a bit, it could seem long, but for ITF it's short. But there's a trick. The presentation, for some weird reason that Phil can explain later on a coffee, was in 3D, but in 3D like the old ways, like you know, the one eye will be blue and the other one will be green. And which I was not there, but it made the content kind of really, really difficult to get. And that's a quote from an email exchange we had after the presentation with many people, including Theo, which is the founder of OpenBSD. The first part, I really like it. It seems that ITF designer did not learn of IPv4 problems. Yeah, that should never have been included. So that's basically what we have been saying with Arnaud since day one. Second part is more funny to me. I think that the 3D presentation at CanSequest unfortunately made a lot of people not understand the full scope and impact of the problem. And after that, it took, I think, basically 2 weeks or 3 weeks for people to actually get, okay, that's super bad. And we discussed with Theo, with Linux people, Cisco people, and a bunch of other smart guys from Google also. And at the end of the day, the routing header type 0 was deprecated. So it means that if you want to use it today, it's not working anymore. So next time, if we do IPv6, IPv7 or IPv8, please don't do source routing anymore, because we did the mistake twice in the past. Node information queries, another weird protocol that we implement in Scapy. This one is strange, bit difficult to implement. The specification is weird to read. The goal is to ask a question to a node and say, okay, please give me your name, please give me your IPv4 address, and please teach me all of your IPv6 addresses. So it's super strange, really strange protocol. And the worst part that back in 2006, 2007, I didn't manage to find the proper year in my archives. Node information query leaked data all over the internet. Because the specification was a bit weird, some stacks, they allow you to ask a question like from Paris to Tokyo. So it was possible for me from Tokyo to ask the name of a server that was in Paris, get also the IPv4 and IPv6 address. It's really bad also for a security perspective, because I will bet it's the same case today. You don't have the same firewall rules in IPv4 and IPv6. So 20 years ago, people will put firewall rules on IPv4 and nothing on IPv6. So if it was possible to actually create stuff on IPv6, you could attack the other protocol. So it's really, really bad. Today, this is restricted to local networks. Most OS don't support it. I didn't do my homework over the weekends. Last time I checked 2 or 3 years ago, only FreeBSD was actually supporting that. You have that in macOS, if I'm correct, but it's disabled. You need to re-enable it with sysctl. Even, yeah, this protocol is weird. It's a bit useless, but still it's there. IPv6 attacks in Scapy. So the ARP, Address Resolution Protocol, was replaced by NDP, Neighbor Discovery Protocol. Completely different protocols, same vulnerabilities. You can spoof. The ARP request is called network solicitation. You can spoof like you do with DHCP. In that case, it's called faking the router advertisements. So it's basically the same stuff. And so Arnaud did some implementation. There are in a specific Scapy function called NDP attack. So if you type NDP attack and press tab twice, you have completion. So all of these ones. The one in green, NDP attack fake router, is also really simple to implement manually, and that's again a good example at how easy it is to use the IP6 implementation. So you write this router advertisement variable, put the router advertisement message on top of IPv6. Then you need to specify the prefix, and we have a function doing that for you in Scapy. So this inet6 underscore function, there are helpers all over the place that helps you to do quick stuff with IPv6. And then that's the specification you need to give your MAC address. So if you send that on a network, so if you do that on the Wi-Fi network, you will pretend to be the IPv6 router, and people will send you data. So why? Because there is this IPv6 preference over IPv4. So if you did not disable IPv6, if someone is playing that tricks with you on a local network, Wi-Fi open network, basically all of your packets will likely go and go with IPv6 to the attacker. So what I did next for this presentation, try to have a look at what I call the legacy of IPv6 support. So that's a list of CVE. So I'm not pretending that we discovered them. I'm not pretending that they were discovered because of Scapy, but at some point, if you read the write-ups, all of them are super interesting. At some point, all of these researchers, they use Scapy to either help them to push the data they wanted in the memory to do debugging and find the root cause. So the first one, the CVE 2024, if I'm correct, the write-up is basically the analysis of the binary diffing between the two versions of Windows, and they are using Scapy to put specific data in structure and then understand what is going on. So it's either for debugging or actually to do the POC. And the last one, for example, is really cool. It makes OpenBSD crash with a fragmentation header. That's unspecific. The way you actually do fragmentation with IPv6 called the fragmentation header. And by playing with the offset of the fragmentation header, they can do arbitrary write on OpenBSD and make everything crash. So you get the blue screen of death, but with OpenBSD, not Windows. So I think it's really cool that people are still using the implementation and finding it easy to interact with an IPv6 stack. Other legacy, this one is a bit more surprising. Some people are actually using Scapy internally to test their IPv6 stack. OpenBSD, they are big users of the IPv6 support, and they do a lot of unit tests with Scapy against their codes in the BSD kernel. So I think that is super cool to me. Other things, people, they develop tools based on Scapy. We have the first one, which is an IPv6 security assessment framework by the German company called ERNW, which is super great. That's a bunch of tools based on Scapy, super simple snippet, but yet you can use it to test an implementation. They made a really good work at bypassing something called RFCs. So what I said before, you can on a network send or pretend to be the router by sending router advertisements. And these days, if you buy a network switch, you have a feature which is called RFCs. RFCs is basically saying that I will disallow every router advertisement on all parts of the switch but one. So it's impossible to actually pretend to be the router. If you know the name, it was called DHCP snooping with IPv4. And they found a way to actually bypass that by using extension header. And because Scapy is so flexible, they did a lot of tests, tweaks, and changed the order of extension headers, and basically they can bypass extension header. Then you have two other tools, super interesting, to do man in the middle with Scapy over IPv6. The first one, MITM6, is mainly focused on Windows. It's doing man in the middle by tricking the target to accept DHCPv6, which is one of the ways to provide addresses to an IPv6 node. And the other one is doing the same, but more generic, using NDP and ICMPv6. These two tools are super interesting to man in the middle, but because we're reaching the end of the talk, I wanted to give you something. I mean, a keynote is not always fun. You need to it's like more like 40 minutes of me like explaining my life, and I'm super old. This stuff 20 years ago, and this is kind of new. I want to show you another way to do man in the middle with IPv6. Something that I think is not known. At least I found it on the way I was giving a workshop, IPv6 workshop at the Kansas Quest conference. I did that for years, and I recall that one way on my way to Vancouver, I was in the plane, I was reading the RFC one more time, and I found that. So if you don't know, we have redirect on ICMPv4. It's disabled. If you have a look at your Linux kernel, Windows, whatever, it will be disabled. Redirect is a way for a router, like the one you have on a Wi-Fi network, to say, okay, by the way, you know, I'm not the best exit point, you should talk to someone else. So that's basically redirect, which is really weird. For an attacker, obviously it's a perfect message because an attacker will spoof the router and say, okay, send everything to me. So an IPv6 specification, it's written, redirect messages are sent by routers to redirect a host to a better first hop router for a specific destination. And then I was in a plane and I looked at the part in green, and this is the crazy part. Or to inform hosts that the destination is in fact a neighbor only, which means that before in IPv4, the redirect will say, send me all of your traffic. And with IPv6, you can say, send me all of your traffic, or, okay, by the way, this one node that I want to spoof as an attacker, and send the data to this node. And then you have the part, the later is accomplished by having the ICMP target address to be equal to the ICMP destination address. And basically, that's, you read the sentence, then you go to Scapy, you send the packets, and you're an attacker. So that's the way you can do the man in the middle with ICMPv6 redirect. That's basically reading the RFC. On line 1, you will spoof the router, so source will be the router. Destination will be the target, the person you want to attack. On the IP layer, sorry, you do the same. Oops, sorry about that. IPv6 layer do the same. Line 3 is that basically the line we have seen in the RFC. You send the IPv6 neighbor discovery direct, and the target and the destination, that's the destination you want to impersonate. That could be, for example, a bank or whatever. And then you just need to put your MAC address in this option. And this is really good because with the other option, with IBEX and MITM6, what they try to do is try to inject a fake DNS router in order to control the name resolution. In that case, you just operate at the IPv6 layer. Only one target, only the traffic to the target is redirected, which means everything else will go through the default router. So an attacker, you are super lazy, there is nothing to do. The victim will, in the end of the day, will talk to the man-in-the-middle target on the local network, so communication will be really, really fast. And as an attacker point of view, he only needs to configure the spoof service. So it's, again, super simple compared to other solutions. When I say it's new, I've never seen that documented anywhere. I never seen that in a tool or in a conference. And I think every time I'm saying, okay, I will talk about that, and when I will go back home, I will write a blog post. And I never did it in the past 10 years. So I wanted to do a demo, but I wasn't sure I will be able to do it. So here you need to stay with me because it's a bit difficult. So we have three parts. On the top left, you have just a ping 6 running. So it's not running because it's an image. Here on the right, you have the neighbor table, and I will explain next what you need to do. And then at the tool, basically sending the redirect with Scapy. So we'll go with box number 1. So we got an ICMPv6 echo reply. You need to notice the TTL, 128. And the time, unfortunately, it's there's a wrap here at the line, but the time is really long, 155 milliseconds. Then number 2, we send the ICMPv6 redirect. So as you can see, that I use the show method in the packet. So here that the destination I want to do the man in the middle for, and then that the MAC address of the attacker node. And then you have Scapy sniffing for echo requests and answering with echo reply. You have the ID and the sequence that you can also see 113 should be that one. Number 3, that's what we call the neighbor cache. It's basically the ARP cache, that's a list of MAC addresses and addresses you can reach on the node. And you can see that my target here, you can see the address ending by 44D7. We know it's MAC address. So this address is in Japan, so there's no way that I will know it's MAC address. So it's fake. So it's the MAC address of the attacker. And then what next? Line 4, the TTL moved from 128 to 64. So why? Because in Scapy, the default value of TTL is 64. So the third change. So it means that here we are talking not the final destination, we are talking to the fake Scapy service. And then the time, it's 4 milliseconds. So with this attack, again, I'm sorry, it's not a live demo. We're able to move this destination far away in Japan to my node really close in the same room and have all of the traffic intercepted by the attacker. Again, here the example was super simple. We only intercept and answer to echo request, echo reply, but obviously you can do everything you want. Yeah. Conclusion, that was a really fun 20-year journey. Most important, I made lifelong friends through Scapy, Philippe, Arnaud, Gabriel, and many more, Niels. We learned on the way many things. I'm really proud to say that we broke a lot of other things, and we shared stuff with others in conferences. We had a lot of discussion. Many stuff we implemented did not actually released. I have a lot of branches at home on my Scapy repository, never released. So I think it's super cool also. Thank you for having me there. And I spent the weekend like, I feel like really old, like to think like on my life 20 years ago. It's a bit strange weekend. So to conclude, we started Scapy IPv6 as a hack in 2005. And I'm sure, I'm convinced that 20 years later, it's still making an impact and people are using it. So I'm really proud. And yeah, mainly that happens thanks to Philippe. So thank you, Philippe.
So thank you very much for this talk.
Thank you.
Thanks for having you here. So now we have the chance to have a few questions and answers. So anyone questions, please? Questions? Okay, here we go.
That's microwave supporting IPv6 from Japan. Sorry.
How do you have so much experience doing changes for Scapy. I only write really bad Python code. And
me too.
You as well. So that's not a requirement. I just recently made an issue on Scapy, I'll talk to you about it later, but it's very timing based. How do we do unit tests that very strictly control the time of the packets that are going in for the testing of Scapy?
You mean testing Scapy or?
Yeah, writing unit tests for Scapy to demonstrate bugs and fix bugs in Scapy that are clearly timing constrained.
I will need to get one more coffee and give you an answer.
Good question. So, looking at the current hardware flying around, if Cisco or not, or Unify, Ubiquiti, whoever is out there, the IPv6 implementations I came across are really bad most of the time, and the user interface, user experience is actually equally horrible. Do you actually see IPv6 going mainstream sometime soon or not? No.
Oh.
It's been now like 30 years plus.
I have a slide that's exhaustion of IPv4. So basically this slide basically means it's not possible for you to get a public IPv4 anymore since 4 years, more or less. There was another slide I wanted to add. So when I did my studies, so again, 25 years ago, the professor teaches about IPNG, which was before IPv6. And the question, so basically it told us that IPv6 will be next year. That was 25 years ago. That will be my main answer. The thing is, it took so long to develop IPv6, to deploy it, to have the stacks on Windows, Cisco, whatever, that network operators, they took other actions. And they have some TGN, carrier grain NATs, they have other tricks to make the IPv4 lifetime longer and longer and longer. So I will not take any bet. So as of today, people are using IPv4 really fine, and some operators, they do some IPv4, IPv6 translation. You have some devices doing that. You have that in Android, for example. The weird stuff, X6lat or something, X4 6lat or something like that. So I don't know.
Okay, thank you.
Thank you.
Any more questions? All right, then. Thanks again, Guillaume, for a great talk.
Thank you.